Okay, so we are here today to talk about our final project for Engineering 11. This is our Huntington Beach TC data project, and we're group 12. So first off, why do we study TC? Well, I mean, if you actually look at the past 40 years, the total coliform levels have been decreasing. But what we have been finding is there are spikes near outlets to the ocean, like the Santa Ana River. So these outlets tend to be in highly populated areas like Huntington Beach, and high TC levels can cause people to get sick. So it's not really the low average yearly or monthly levels we're concerned about, it's the spikes and the probability of having a spike. So the next question is, what causes these TC spikes and how do we control it? So what we're going to discuss in our project is how we prepared some CDFs from the data gathered and compared them. We're going to fit some analytical distributions to the 3 CDFs from 3 different stations and find the parameters associated with those. Then we're going to do similar type testing for salinity and temperature data, fit some more analytical distributions, and then just measure some extremes at all 3 data sets, just determine the correlation between them, propose a hypothesis test. So first part, organizing data and plotting the CDFs. So part 1, our group was tasked with analyzing different data from Huntington Beach and the total TC it has. So our data was from 1991 to 1994, and this included some sensor data as well. So the measuring device went down to 20 TC and all the way up to 160,000, but you know, there could have been values below and above that. It's just the data, you know, couldn't be measured, and also there was some missing data in between as well that we had to account for. So first off, just analyzing the different stations. So we had this equation for finding the CDF. It was basically the number of occurrences for a particular level of TC with regards to the total number of samples that were taken. So that's our north CDF, our north station CDF. The next, this is our south, and here's the 0 station. So what we wanted to do now was compare all of them together. So we put them all on the same graph. So if you look at the graph here, the blue is the Santa Ana River outlet, the green is the south station, the red is the north station. So if you look at this next slide, we actually have some numbers that we kind of look at. So if you take a value, so we kind of just looked at ln of TC of 3.8. What the y-axis, what the y value is giving you is the probability of finding TC values that are less than that. So for the 0 station, you have a 60% chance of finding concentrations that are less than 3.8. So if you want to have more, if you want to find the actual concentration being more, it's 1 minus the probability of x less than 3.8. So there's a 40% chance of actually exceeding that concentration. So what that means is if you look at the south station, if you look at the north station, since those are at a higher probability of finding a lower concentration, that means those are better areas to recreate in. The north station will actually be the best one to recreate in because you have the highest probability of having the lowest concentration of TC. So next was part 2, and I'm going to let Darren take care of that.
All right, so for part 2, what we basically did, all right, so this is the tools we used first for finding parameters. All right, now moving on to the next slide. So here in the next slide, we can see our calculations. So in order to solve for the parameters, we calculated for lambda and zeta by picking 2 points on the CDF and setting them to each other by using the log normal distribution equations. Okay, and so basically in this case, we used these equations right here. And then we picked points right here, these 2 points, we plugged them in. And then using the tools we had from this part, we solved for it. And so on to the next slide. Okay, so after all the number crunching, here's what we got for our parameters for the north normal CDF of the log transform of TC. So as you can see, we have here lambda and zeta. And once we got these values, we plugged them in to our error function. And then what we did is we graphed this error function to give us the best fit line compared to the empirical CDF. Also, we did the same for the south and the 0 station, which is the Santa Ana river. Okay, so CDF fitting conclusions. In conclusion, we created the best fit lines because the best fit lines for the CDF provide a better representation of the actual probability of the empirical CDF, which will help us better decide on which stations is the best station to recreate at. In addition to best fitting the CDFs, we did the mean comparison test. So basically how we did this, we used the equations from lecture and then we put those equations into MATLAB. Feel free to look at MATLAB to refer to our work. But in the end, here are the numbers we got. So we solved for mean, variance, and here's the percent error tolerance we worked with, which gave us these values. Since this is a two-sided distribution, we divided 0.05 but in half, and then here's the number we got. So in order to figure out what to recreate, we would compare the TC means of the three stations, the combined north station, Santa Ana station, and the combined south station. With the error tolerance of 0.5, we ended up with a graph like the one on the right. Okay, so what was the point of solving for all those variables? Well, we used those variables to then solve for the t-statistic. So the t-statistic reveals whether the two samples from different stations are drawn from the same population. So after we calculated the t-statistic, we realized the following answers. And based on our answers, we can conclude that the t-statistics of north and south are from the same population. Basically, why? Because if you look at these values, you see that the north and 0 right here exceed the tolerance limits, and 0 and south also. And what this means is basically that their means are very different from each other. So if you look, the mean of 0 is very different from the mean of the south. It almost doubles it, and also like the same with the north station in 0. If, however, you look at the south and north, you'd see that they're very similar, so that they fall within the tolerance we established earlier. Okay, so the follow-up question. Okay, when we compared parts 1 and 2, the data was by no means perfect, but the values we got in part 2 are consistent with the more qualitative result in part 1. Based on our analytical approach on part 2, we can support the assumption that the north station still seems to be the safest to recreate in, since there's a lower probability of finding TC.
Okay, so back to Austin. We're on to part 3. So finding and fitting the CDFs of salinity and temperature. So the first part of part 3 was to do something very similar to what we did in part 1. We just wanted to find CDFs. So we made a CDF for temperature and we made one for salinity. But in addition to that, we also wanted to find some other best fit analytical graphs to sort of match that data. So as you can see here, we have our temperature data and pictured our few different analytical graphs. And the best fit ended up being the log normal distribution. The log normal is this red line right here, very close to the normal distribution. So if you look here, we have our MATLAB code. This is how we found and put the different graphs together. And then we had our adjusted R2 values to actually find what the best fit was numerically. So we had a MATLAB script that calculated these. And essentially, the closer a value was to 1, the better fit it was. So if you look, 0.9873, that's the closest to 1 out of these 3 values. So our log normal ended up being the best fit. Next, we have our salinity here. We have our salinity CDF with some more analytical graphs on here. If you look at this dark black line, this is our beta distribution. That ended up being the best fit to our salinity CDF. So if you look again, MATLAB code for the different analytical graphs and our adjusted R2 values. If you look, 0.8277 for the beta, R2 adjusted, that was the closest to 1, so that ended up being the best fit there. So next, on to part 4, where we're actually finding correlation between the data and forming a hypothesis test. So the first thing that we did for that was finding an exact distribution. So essentially what we're doing here is we have n, which is just a random size, well, a random sample size that we're taking from our data. And then we have this MATLAB code. So with this different sample size and then iterations we run it to, we take our values of lambda and zeta. These are parameters here that we got from earlier in testing. And we'll run this MATLAB code. And if you look at this page here, these are the graphs that we got. So we had an empirical CDF, we have the exact CDF. So based off the end value, the number of random samplings, we actually got pretty different results. So if you look at the difference, what the trend you kind of notice is that the higher N you have, the more concentrated the values get. So if you look at N equals 100, we're more focused towards between 8 and 10. And here we're kind of spread out a little bit more. If you look here, these are kind of the extreme ends. N equals 1, we actually get just our normal CDF that we had earlier in the slides. And if you look at N equals 738, this was actually the highest TC concentration we had. It's all concentrated towards 12. So that's sort of the trend that we noticed with our data.
All right, so continuing on the trend of finding a correlation between the data, we used, in this case, conditional probability. So when we use conditional probability, we used extreme values. And how we considered these was that we picked the top or bottom 15% of the sample data as extremes. So in the end, we ended up with TC being greater than 1,000, conditioned on temperature being greater than 15, and salinity being greater than 31 as our conditions. And the way we solved for it was we used these formulas, the conditional probability formula, which was on lecture, and the variation formula, which was also on the lecture slides. And we have a MATLAB program which ran these. So if you want to see the calculations, feel free to go ahead and check it out. All right, so on this slide, we have the probability data of the north, or of the stations, condition and the conditional probability, temperature, and salinity. So if you just look closely, you'd see that these numbers, they have a certain pattern to them. So from N15 to 0, you'd see an increasing pattern, and from S3 to S15, you'd also see an increasing pattern. Same with the salinity. So if we actually take a look at this and we graph it, we would see this trend right here. So the really cool thing about this is that this plot actually supports our initial assumption when we said that recreating at the north would be the safest and best option. Because if you look here, these first 4 points represent the conditional probability of the high TC in the north. So if you add all these up, it'd still be lower than the conditional probability found when at the Santa Ana River, and the conditional probability found on the south. Same here with the salinity. So basically what we're getting off of this is that the conditional probability of the north is less than the conditional probability of Santa Ana River and the southern stations. And if you look also, you'd see that these conditional probabilities are extremely low values, which could also imply that the conditions don't even matter when determining TC being greater than 1,000. All right, so to add on to that, we did hypothesis testing for proportions. And in order to test for proportions, we used the following equations. So first, we set our hypothesis, our null hypothesis, and our alternative hypotheses, and we used this right here, the z-score formula, to find or to determine whether we accept we reject the null hypothesis or reject the alternative hypothesis. So in this case, we use the 5% error, which is distributed into 2 tails. So we have a 2.5% error tolerance on each tail. And when we plot our numbers in, and this is for our hypothesis testing for the temperature, we would see that this falls within the tolerance. So in this case, we reject the alternative hypothesis. And we'll get to, we'll talk about what that means in a few slides. And the same here for hypothesis testing for salinity. Based on the z-score values we got, they all fall in like this little concentrated area right here. And in this case, we also reject the alternative hypothesis. So here are the results. After solving for the hypothesis testing, we came to the conclusion of rejecting the alternative hypothesis. The alternative hypothesis basically states that the proportions are different from each other. And by rejecting the alternative hypothesis, we concluded the proportions are drawn from the same population, and being from the same population implies that there are no outside elements found on the other stations that could possibly affect the probability of TC being greater than 1,000. So all in all, the comparison of proportion and hypothesis testing further validates our initial assumption on recreating on the North Station. Moving on to conclusions. All right, here, conclusion. Overall, we have decided that the best place to recreate is at the North Station because those stations contain the least amount of TC as seen on the empirical CDF graphs. However, it wasn't enough to fully support our claim. So in addition, we supported our initial hypothesis of recreating at the North by doing a mean comparison test, a comparison to proportion test, and hypothetical testing. According to our mean comparison test, we realized that the TC mean of the North stations are a lot lower than the ones on the other stations. Moreover, to further support our hypothesis, we tested extreme values of TC conditioned on temperature and salinity using conditional probability. And once we got the conditional probabilities, we then used those to determine whether temperature or salinity will affect TC being greater than 1,000. And what we got was that temperature and salinity barely affected TC being greater than 1,000 as seen on our conditional probability graph. After solving for the hypothesis testing, we came to the conclusion that the samples we took were from the same population, meaning that temperature being 15 or salinity being greater than 31 does not affect TC being greater than 1,000. However, we need further testing to determine whether temperature being less than 15 or salinity being less than 31 will actually affect TC being greater than 1,000. So here's our speculation on why we think the TC probabilities are distributed that way. Since in our case, more TC's concentration can be found in the Zero Station or the Santa Ana River, we concluded that TC originates from sewage runoff carried by the Santa Ana River to Huntington Beach.
All right, that was our project. Thank you very much. And thank you.